Good morning, class. I hope you're doing well. So we're going to start talking about logarithmic functions, and I know there's some equations that you found in your homework from yesterday, where you had to do say 10,000 is equal to 2.68 to the power x, and at this moment we haven't yet learned a way to solve this algebraically. And one way you can solve these equations is to use logarithms. So today we're going to start talking about logarithmic functions. I told some of you that you can use the natural log, which we'll talk about, or the logarithm to the base 10, which we'll also talk about. Now, back in the day, before the invention of calculators, people had to do all sorts of ridiculous calculations by head. Scientists had no other way of figuring out how to calculate numbers like 32184 times 0.0436, 7. Just imagine any kind of ridiculous calculation they had to do by head. They had to write this out and do long multiplication every time they had to do these calculations. And it got harder the bigger the numbers got, the harder the calculations got. So some guy called John, I think he's called John Napier, sounds French, and some other guy called Henry Briggs. I think you've heard of Henry Briggs because he's had a couple of other mentions in history. Henry Briggs, even in physics, some things are credited to him. These guys invented, especially this guy, John Napier, invented the logarithmic scale, or the logarithmic scale as a way of multiplying large numbers by simply putting their answers as powers to the base 10. For example, there's a particular base to which I can raise 10 to get this number. Using your calculator, you can figure out what that base is. But if I estimate here, I know this is like 4. How many decimal places are these? 1, 2, 3, 4, 5. So I know that this number is between 400,000 and 500,000. This number here. So it's between 10 to the power of 4 and 10 to the power of 5, right? So if I know that it's between those powers, I can just go on increasing the power of 4 by say 0.1, 0.2, the power of 10 to 4.1, 4.2, 4 point something, until I get a number that's exactly this one, right? It will be to a couple of decimal places. I don't know, probably 189 something, but this is what this guy John Napier, this is the kind of system he invented, and that helps you to multiply large numbers, because if you have a large number like this, then all you have to do, he invented this scale, made some tables called logarithmic tables. This guy is the one who helped him expand those tables, and then you could look up any number you wanted to multiply in those tables using logarithms. So this was very helpful because like I said, scientists did not have calculators yet and still needed to do a lot of arithmetic. The particular field that it was created for was to help in multiplication of signs. So like sine of 43, we know it's a fraction that is, I think it's a fraction that is not terminating, non-terminating fraction. I don't know what that is, but if you look it up on your calculator, it's a non-terminating fraction. So it was developed basically to help with multiplication of signs, because the field of trigonometry was growing fast at that time. So this is old mathematics, and logarithms, one application of logarithms right now is I don't know if you've heard of hope I'm spelling it right, the Richter scale. The Richter scale for determining earthquakes, the magnitudes of earthquakes. That scale is based off of the logarithmic scale, because on the Richter scale, if something has a magnitude of 7 and something else has a magnitude of 9, for example, then this is the 9 is 100 times bigger than the 7, not just 2 points higher than the 7, but it's 100 times bigger than the 7, the magnitude of the earthquake. And this tells you that the magnitude of 10, the magnitudes of 10s between the 7 and 9 is 2, because 100 is a magnitude of 10, that is 2. What am I saying? The power of 10 between 7 and 9 is 2. So if I'm thinking of this as powers of 10, if this is 10 to the 7th and 10 to the 9th, then the difference is 10 to the 2nd, which means that that's 100 times bigger. So that's one of the applications. However, in modern day today, something called the natural logarithm, which we write as in, not ln, write as in, the natural logarithm, is what has remained useful the most, this natural logarithm. Some calculators have ln. I think your calculator has ln, but it's called the natural logarithm, in. So let's start talking about logarithm. So in the modern day today, this is what's used the most in physics, in chemistry, radioactivity, even in mathematics. But the old logarithms to the base 10, besides the richer scale, I can't think of any other application. You guys can look that up and see if there are any other applications besides the richer scale. Okay, so let's look at these logarithmic functions and see what they're all about. Definition of a logarithmic function. So a logarithm of base b of a positive number x satisfies this definition. X has to be bigger than 0, b has to be bigger than 0, and b cannot equal 1. I'll explain why. So it's read as logarithm of b, of base b, power x is equal to y. Logarithm of b, logarithm of x to the, you can read it as logarithm of x to the base b is equal to y, or you can read it as logarithm of b to the power x is equal to y. And that can simplify to, this is what it means algebraically, is that if I raise b, if I take b and I raise b to the power y, my answer will be x. So if I take this b and I raise it to the power y, my answer is going to be x. So this kind of backward cycle is going to help you figure out how to name your logarithms. What that means is, what power, if you're looking at logarithm of b, logarithm of x to the base b, you're asking yourself, to what power is b raised to give me x, right? To what power is b raised to give me x, which is the same thing here. To what power is b raised to give me x? What power do you raise b to get x? We'll look at some examples. Now this x has to be greater than 0. X has to be greater than 0 because you can't have a logarithm of a negative number. What do I mean? Because this whole logarithm equation simplifies to this meaning here, that to what power is b raised to get x. X cannot be a negative because there is no number that you can raise to any power to get a negative number. I hope that makes sense. If this was negative 3, and let's say b was 2, and y, I'm looking for the value of y, there is no power to which I can raise 2 to get a negative number, right? So x cannot be negative, and that means that we cannot find the logarithm of a negative number. B has to be greater than 0. B has to be greater than 0. The base can also not be a negative, because it's not always going to be consistent to raise a negative base to, if I can't always raise a negative base to something to get a positive number, right? If x has to be a positive number, then there is no negative base that I can raise to any power to get that positive number. I hope it makes sense. I cannot raise negative 2 the base cannot be negative, basically. So yeah, b also cannot be equal to 1 because the logarithm of 1 is 0. So every time you find logarithm of 1 to any base, that's going to be equal to 0. Alright, I hope that's a sufficient introduction. If you have questions about anything, please send an email or comment if I see it. And don't get hung up on this, don't get stuck here on this page, because this is just definition of logarithms. What's important is the application which we're getting into. Now if you graph the graph of log x, if you go to your calculator and graph log x, log to the base 10 of x, this is what it would look like. And because that's what the graph looks like, this is the graph of the logarithm of, say, 2 to the base x, and yet this is the graph of 2 to the power x, right? 2 to the power x, the graph is that way. Logarithm of logarithm of x to the base 2 is this one, and we know that if these two lines, if two graphs are reflected over the line y is equal to x, that means that those graphs or those functions are inverses. So that tells us that this function 2 to the power x is an inverse of this function log of x to the base 2. So that means this log of x to the base 2 undoes what this function does, or the other way around. 2 to the power x undoes what log x2 does. That tells you that if you take the logarithm to the base 2 of logarithm to the base 2 of 2 to the power of x, right? Because if I'm taking the logarithm of this function, if I'm evaluating gx of f of x, that should give me x, right? That should give me x because the functions are inverses. If I was evaluating logarithm of 10 to the 10 to the power of x, again I expect that to be x. I hope that makes sense. Because the inverse function is the function of the other function should equal x, which is the true meaning of inverse functions. So every time we're going to find some practice questions like this. If you're evaluating the logarithm of a number, if say this is a and that is a to the power x, this is always going to be equal to x. And a better definition, a better explanation for this will come when we're talking about properties of logarithmic functions. Alright, moving on, let me make this smaller, see how that works. So we have an example here. Write the following equations in exponential form. Before I even go there, remember the logarithm of x to the base b is equal to y. That equation is the same thing as asking yourself, to what power do I raise b to get x? So you do that cycle thing that I did at the beginning. To what power do you raise b to get x? So when you do that, you'll find that the equation that you have written will be b to the power y must equal x, right? So it's just asking us to write them in this form. So since it's asking us to write them in that form, you can go the old school way and ask yourself, what is the b, what is the y, what is the x? According to this, the 4 is the b, the q is the x, and the m is the y. And then you can just write your equation as 4 because 4 is b to the power y, I'm following this right here, to the power y, which is m, is equal to x, which is q, which is correct. Or you can do the cycle. This goes to that, and then that goes to that, so that will still be 4 to the power m is equal to q. Okay. Now, every time you see a logarithm that's written without a base, every time it's written without a base, that base is like base 10 because it's referred to as the common logarithm, and you can blame those earlier scientists for this. It's just known as the common logarithm and it's the base 10. So for simplicity, if the base is not written, then that is base 10. It's the common logarithm. So in this case, you can see that the base is 10. The y value is this t, right? And the x value is v, right? So you can just do the cycle and go 10 to y to x or to v. So it's going to be 10 to the power t is equal to v. Or the definition of the logarithm itself, to what power must I raise 10 to get v? To what power do I raise 10 to get v? That is the logarithm of v to the base 10. So this you just say 10 to the power t is equal to v. Write the following in logarithmic form. Alright, so 4 is raised to the power of x to get y. By the definition of a logarithm, the logarithm of x to the base b is asking you to what power do you raise b to get x, and the answer is that power. The answer is y, which is that power. So y is the power to which you raise b to get x. Now since this is already given as 4 to the power x is equal to y, this tells me that I raise 4 to the power of y, right? I raise 4 to the power of y to get x, which is the logarithm of 4 to base x. If this is confusing, just remember a, b, and x up here. Sorry, just remember b, x, and y. B, x, and y. So the b is the base, which is the 4. The y is the... Wait, this is 4 to the power x is equal to y. 4 is raised to the power of x. I got this wrong. 4 is raised to the power of x to get y. So this should be logarithm of 4. Logarithm of y to the base 4 is equal to x. And I was saying that if that's confusing, just like it confused me, identify the b, identify the x, and identify the y. Now this one is a little bit switched because the y is, the x is this, is the answer, and the y is the power, right? So then if you want to write log bx is equal to y, then you have log of x, and remember the x is y, to the base 4 is equal to x. This reads as 4 raised to the power of x gives you y, or logarithm of 4 to the base, logarithm of y to the base 4 is equal to x. Alright, what about this one? To what power do I raise 10 to get b? That will be logarithm, the base will be 10. To what power do I raise 10 to get b? Since what I'm getting is b, the b goes here, and then the a goes there. Identifying the b, this is the base, so that's the b. This is the answer, so that is your x, and this is the power, so that's your y. So then you can still just write it as log y, which is the, log answer, which is your x, log of x, which is b, to the power of 10, which is that 10 over there, is equal to a. You can always check your answer. Does 10 to the a equal b, what I have here? Yes, that's what you have. How do I solve for logarithmic equations? I can convert to exponential form. So I go to that, and then I go to this. So to what power do I raise 3 to get x? That's what this is asking you. To what power do you raise 3 to get this x value? So this is going to be 3 power 2 is equal to x. So x is just equal to 9. And this tells you that the logarithm of 9 to the base 3 is equal to 2. And I hope you can see that this definition of a logarithm, to what power do I raise 3 to get 9, right? That power is 2. That power is equal to 2. The logarithm of 9 to the base 3 is equal to 2. What about this one? This is a common log because the base is not given. So this is just going to be 10 to the minus 3 is equal to x, because you're using that cycle thingy. So 10 to the minus 3 is x. X is equal to 1 out of 1000, or if you want, you can write 0.001. How about this one? This is asking me, to what power do I raise 3 to get 1 out of 27? Now I can simplify 1 out of 27, because 1 out of 27 is the same thing as 3 to the negative 3. How do I know that? 27 is the same as 3 to the power 3. And I know that 1 out of 3 to the power 3 is the same thing as 3 to the power 0, and this is taking you back to 9th grade. Divide by 3 to the power 3, which is 3 to the power 0 minus 3. Division is subtraction of exponents. So it's just 3 to the minus 3. That's why I have put that here. So it's asking me, to what power do I raise 3 to get 1 out of 27? Right? To what power do you raise 3 to get 3 to the power negative 3? That answer is very simple. That power is negative 3. Right? Because if I have 3 to the power negative 3, I'm absolutely going to get 1 out of 27. 1 out of 27. Okay, so I can just work that out mentally without using a calculator. To what power do I raise 3 to get 1 out of 27? And that's what you have, right? So if you want to solve it really, you can have 3 to the power, let me call the power x, gives me 1 out of 27, right? This is writing an equation for it. So 3 to the power x equals 1 out of 27. Remember, it's the same as 3 to the minus 3. So that means x is equal to minus 3. Because if the bases are equal, the powers have to be equal. Alright, this one. So I have log 2 1/8 plus 4. Ask yourself, to what power do I raise 2 to get 1 out of 8? Right? Because I'm going to first deal with this, then I'll add 4 to my answer. So dealing with this, to what power do I raise 2, right, to get 1 out of 8? To what power do I raise 2 to get 1 out of 8? 1 out of 8 is the same as 2 to the negative 3, still following this idea. Just replace the 3 with the 2, and replace the 27 with 8. Oh, here we are. So I hope you can see that x is still negative 3, because 2 to the power negative 3 is 1 out of 8. You can check that on your calculator, but you can't use a calculator. But yeah, 2 to the power negative 3 is 1 out of 8. So I know that this whole term simplifies to negative 3, and then I'm adding 4. So my answer to this is 1. Obviously, expect a quiz where you won't be using a calculator, so please practice how to mentally do this without a calculator. Now, moving on to the natural logarithm. A logarithm with base e, because e is the natural number, because remember, e was the natural number 1 plus 1 out of n to the power n. And this natural number, as the n value goes bigger, you can keep substituting like 10,000, 50,000, 1 million. You'll find that this number goes to 2.7182 something something something. So it gets, that is the decimal that you keep going to when n is going up, or when n is going to infinity. So that number can be used as a base for a logarithm, right? And that logarithm is called the natural logarithm. And this natural logarithm has a lot of applications today, and you'll find them a lot in calculus, or if you're doing physics, if you go into radioactivity, carbon dating, trying to figure out how long something has been in existence just by looking at how much of the mass of the material is left, and knowing the atomic number, I think. But yeah, you can use this. This is used a lot in carbon dating, in radioactivity. So this natural logarithm has a lot of applications in the world today versus the common logarithm of the other base 1 to 10 logarithms. Alright, moving on. So if it is y is log e to the power x, that is written as the natural log, and I don't know why the letters in were chosen for this. I think initially it was lin, but then yeah, I don't know, maybe this is some French way to write natural, but I can look it up. It's written natural log x, in of x, and that's the same thing as, because if you do the opposite, if you do the cycle thing that we were talking about, if log of e power x is equal to y, then e to the power y is equal to x. So e to the power y equals x, and natural log of x are inverse functions. That means that the natural log of e to the power x will always give you x, because they are inverse functions. Alright, so we have an example here. use the definition of common natural logs to simplify. All right, I've just talked about that the natural log and e to the power something are inverse functions, right? If they're inverse functions, then natural log of e to the power y should equal y, because that's the definition of inverse functions. The inverse undoes the function. So in this one, the natural log of e to the power negative 5.03 should just be negative 5.03. I don't need to do any calculation on this. It's just an inverse of a function. It's like taking the square root of 2 squared. That's just going to equal 2. Or the square root of x squared should be x, because the square root and the squared are inverse functions. Alright, what about this one? Remember, it's a common logarithm, so it's base 10. So I have 2 logarithm to the base 10 and this number 0.001. And remember, the definition for this is, to what power do I raise 10 to get 0.0001? 0.001 is 1 and 4 zeros at the bottom, right? 4 zeros. 1, 2, 3, 4, 5. No, it's 3 zeros. What? 1, 2, 3, 4. No, it's 4 zeros. Okay. So, to what power do you raise 10 to get 1 out of 10,000? That power is negative 4. I hope that makes sense. The answer to this expression, because this expression is asking you, to what power do you raise 10 to get 1 out of 10,000, and that power is negative 4. Let me show it to you here. Log of 10 to the power 0.0001 must equal something, and that something is what is going to be multiplied by 2. If you use the cycle, 10 to the power of x must equal 0.1231. 0.1231 is the same as 10 to the negative 4, 10 to the x. Since the bases are equal, x has to equal negative 4. So you have 2 times negative 4, which is just negative 8, as the answer to this whole expression, right? 10 log 17. Now, log 17 is, since it has no base, it's the common logarithm of base 10. And remember, the function 10 to the power x is an inverse of the function log to the base 10 of x, right? So if I take 10 of log to base 10 of x, the functions are inverses of each other, my answer is just going to be x. So my answer here should just be 17, right? It should just be 17 because the functions are inverses. E to the power natural log 2.01, same idea, they are inverses, so the answer is just 2.01. This is your homework. I hope if you have any questions ready, please send me an email or